Before we leave the subject of this project for too long, I want to take a minute to go over some more of the underlying aero theory for those of you who would be interested in that. All of this aerodynamic theory goes back down to all the way down to the Biot-Savart law. That is the velocity induced at a location is equivalent to the magnitude of the circulation gamma divided by 4 pi, the cross product of the length of the element of circulation under consideration, and the radius vector to the point under consideration, all divided by the magnitude of the radius cubed. So really you could use this singular law, the potential flow-based law, and integrate all of the necessary influence coefficients for all of Prandtl lifting line theory. It's possible. They undergo several simplifications, looking at what it would be for a straight line of infinite length, so a vortex filament that goes infinity up, infinity down in a volume. They then consider if it was not infinite, if it started at a particular point, maybe the tip of a wing, some termination point in the flow or some turning point in the flow, it went back to infinity in the other direction, then the integration of the velocity becomes a little bit simpler. Velocity is just gamma divided by 4 pi times h, where h is a spacing parameter. So they eventually go through these simplifications and start applying it to wings. The first trial they performed was they being Prandtl and his aero nerd buddies back in the day, without Matlab, just doing everything by hand and paper. For simple wings, with one bound vortex, what would the downwash sheet look like around this wing? They tried to get a converged solution for the entire thing, try to show that their theory was applicable, and it just didn't. It wouldn't converge. They tried with one filament, so constant vorticity from the right-hand side of the wing going across the wing itself and emanating again from the left-hand side. Of course, 2 tornadoes rotating clockwise on the left wingtip and counterclockwise on the right wingtip makes a lot of downwash in the intermediate region. Outside of the wingtips, it's actually upwash. You're pushing the air up. There's an advantage to flying out there. But in the center, at least, it's just all negative. It's all bad. So this particular distribution is for one horseshoe vortex. Is what we call those, right? It looks kind of like a horseshoe. It makes a U shape, emanates to infinity in both directions. So a horseshoe vortex bound on a wing, that's what the downwash distribution looks like in between those elements. And then if you put that in equation form, this is what the integration looks like. At any point y along that line w, which w is the wing bound vortex, you can get the induced velocity in the w direction along that line y, bound by that formula. So they expanded this theory. They said, okay, if one vortex isn't going to be enough to describe what's going on in a wing, what if we started stacking them? So they took one vortex and ran from the left wing tip all the way across the wing, emanated from the right wing tip. Took another vortex from just inside the left wing tip, all the way across the wing, went back from the right wing, just inside the right wing tip. Then a third, kind of towards the middle, across the wing, and left just barely to the right of middle again. And what this means is that you end up with, in some places, multiple vortices stacked along the wings, and this starts to let you define a distribution or a variance in strength of vorticity across the wing. So what you see in discrete form here in the left picture is actually followed in a continuous form over here, where instead of little discrete 3Z, 4Z type counts across the wing, now you have this infinite count of variation of vortex strength across the line itself. So this is kind of differential form. This would be the continuous form of the same type of theory and equations. So if the distribution of vorticity is infinite and continuous, then the sheet emanating from the back also must be continuous. And what that means is where we had discrete steps here between elements describing the discrete change of vorticity emanated, now it's the slope of bound vorticity on the wing dictating the magnitude and strength of shed vorticity behind the wing. So again, they took this and integrated it up now for an entire vortex sheet, and that's where the derivative of gamma with respect to y across the wing gains such prominence, because that controls the magnitude of vorticity shed at that location, and stronger vortices at a particular location generate more downwash on everything else adjacent to it. Keep in mind, vortices affect most strongly that which is closer to them. It's like a 1 over r type drop-off. So all of this is summed together. You move from that definition on the previous page of W, you then look at what W means in terms of angle of attack If the wing is creating a vertical flow motion on itself, its own self-influenced downwash, then you have to take into account that change in angle of attack. This is the equation that tells you why a wing is essentially flying up its own generated hill. You have negative W divided by V infinity. That's the angle between the vertical component of velocity and the V infinity flight speed of the airplane. That, of course, is simplified here in the book through small angle theory, but there's really no need to if you're going to be doing this through numeric solution. So alpha I in the end, so they've just redefined the equation for downwash W, we see here in the bottom of the page, into an angle of attack equation here, scaling it through this intermediate equation 516. So combining that definition of alpha I with what we know to be true through aerodynamics, that the effective angle of attack, the effective lift producing alpha, is the geometric minus the induced. You just take your definition of effective angle of attack, that which is actually producing lift, and then the only thing you have left unknown is the geometric, but that's okay because that was your definition at the beginning of the problem anyway. That's what they solved for. So the geometric angle of attack equals, this is your lift producing alpha. That is your alpha CL naught, so that is the angle at which you produce no lift. And then that is the term describing your induced angle of attack. So those are all of the sources of alpha at a particular wing slice, subject to Prandtl lifting line theory at least, that are being counted for all at once. So that is the path from origin of Biot-Savart law, in quick form, admittedly, to the governing equation of your project. Then, if you haven't already made the connections, once you know what the distribution of gammas are, you can simply take gamma v, rho v gamma, get the prime lift. That means lift at a particular element location. You can integrate across the wing for all of the different gammas and obtain total lift of the wing. You can do the same thing here for induced drag, where induced drag is defined as the L prime times sine of alpha induced. So the alpha induced equation was given to you on the previous page. The derivative, is that fair to say? I should say the local induced drag for that element, d prime I, is described there. So of course you can do the same thing again. Integrate all the way across the wing, circulation multiplied by the alpha induced at that particular location, and obtain a value for the total induced drag of the wing. That's a critical part of your project. In fact, the final step after you've determined the converged gamma distribution. So the textbook goes on to consider things like elliptical lift distributions. It goes on to consider how to properly apply Fourier series to general lift distributions, which, by the way, this is how Prandtl found the solution to this development of theory without using computers. He put everything in terms of these unknown coefficients an and a Fourier series, and came to some simplifying knowledge about what type of distribution is correct and best for a wing. So what he was able to do without a computer over 100 years ago was really impressive feat. But now you have a powerful computer, a powerful piece of software, so we should expect more from you, right? Well, we should expect enough. I think that this is a challenging problem that for many reasons, some of which were seen in the code, some of which were seen in this aerodynamic background, some of which were just in the problem statement. It can be challenging to understand, challenging to implement, and hopefully you obtain some numeric skill to take with you after completing this hard project.